So for most wells, water won't rise on its own. Typically, the water table does not change dramatically. It will fluctuate between 1 and 2 meters, but not much more than that, except in some cases, I guess, which we'll talk about later. But usually, it won't change enough for it to rise all the way to the surface of your well. There are some exceptions to this rule though, and the water will in fact rise through the well and go all the way to the surface in cases where your well is called an artesian well. So said wells are abundant in a region of France called Artois, and that is where also you get the Stella Artois water. And so we call these type of wells artesian wells after the region of Artois. So the term artesian is then applied to any situation in which groundwater, which is under pressure, will rise above the level of the aquifer. Usually, two things need to be met in order for an artesian well to occur. The first thing is that the water is typically confined to an aquifer that is inclined, so that one of the ends can receive the water. And then the second condition is that the aquifer must be confined by two aqueducts, one above and one below it. So overall, the aquifer needs to be an inclined and confined aquifer. Again, through which one of the ends of the inclined aquifer water is being recharged. So when the layer from the overlying aquitard is tapped, as you're seeing in the image over here, the pressure created by the weight of the water above forces the water in the well to rise upwards. Friction will play a role within this scenario. So if, for example, there was no friction at all, the water in the well would rise to the well or to the water level in the aquifer regardless of the situation. But because friction does occur in any one place usually, the further the recharge is from the well, then the greater the friction will be and the lower the pressure that there is in order to push the water to rise. So also the lower the water level. So I know that was a little bit confusing, but let's try to picture it based on the image. So because friction does occur in between the two layers that are surrounding the aquifer and even within the aquifer itself, the water is not going to flow freely from the recharge area on downwards onto the well where it, because of pressure, will rise upward. So if the recharge area is a little bit closer to that well, say around here, then it will be a lot faster for it to not have as much friction and because of pressure still rise upward to the new water level. But in cases where the recharge areas are a lot further, there's a lot more friction involved because it has to travel through all of those grains and all of those sediments and be near those aqueducts, which are also providing resistance and friction. So overall, there won't be as much water pressure involved after all that friction, and so the water that rises through the well won't rise as high as in the first scenario. If that is still a little bit confusing, re-listen to what I just said, and then I also encourage you to read your book a couple times or 3 times while they go through this explanation. That might clarify things. So there are flowing artesian wells and non-flowing artesian wells. The flowing artesian wells occur when the well is below the pressure surface. So you're seeing the pressure surface line outlined here in the graph, which is basically the water table at the highest point of the aquifer. So again, flowing wells will happen when the pressure surface is above the well, like it is in this case. And then the non-flowing artesian wells will occur when the well is above the pressure surface. So if it was the case that your well didn't lie here, but it laid over here. Actually, yeah, perfect. So the well number 1 in this case, you see that even though the well is right at the pressure surface, it's not flowing because the top part of the well is not below the pressure surface. So although it is touching fully the aquifer and it is under pressure surface, it is non-flowing. The water isn't rising all the way up through the well. So sometimes artesian systems are simply present as natural springs rather than wells that we drill. Natural springs will exit the ground surface through fractures like faults that cut through the impermeable aquifer confining layer above. Examples of this are pretty rare nowadays, but they used to be more common before we used groundwater to the extent that we have in the last century or so. So there was one artesian well, for example, in Pullman, Washington. If you have been to Pullman or know about it, it's where Washington State's university is. And actually back then it used to be like the main thing about the town, and so this little image here was one of the souvenirs from Pullman's artesian flowing well. However, now the city of Pullman is trying to figure out a solution to the continuous lowering of the water table from the Palouse Basin aquifer system that is ongoing. So the whole Palouse Basin aquifer system has been lowering in water table levels, and which is pretty concerning. So a few of my professors at the University of Idaho had been working towards not necessarily a solution, but an explanation to how it is that the water is being transferred and how fast it is flowing to the aquifer from the recharge areas. Another area where natural springs used to be was near the Black Hills of South Dakota, for example, which is the image up here. The Dakota sandstone, which is this kind of beige-looking, yellow-looking, tan-looking shade of rock, acted as the aquifer where the water was stored. And it was confined by the limestones below, so you're seeing the Madison confining limestone. Madison group is also a limestone. And then these Paleozoic rocks, for the most part in this western area, are limestones as well. And then it's being confined above by the shales, by the Skull Creek Shale and by the Cretaceous Shale, which are both confining this aquifer of the Dakota sandstone. So as you're seeing, this area, this recharge area, is much higher than the areas down here. So if the pressure surface were to be just a little bit below that recharge area, say around here, then all of the areas down here could have natural springs flowing from the water rising up towards the surface. Okay? We'll go ahead now and talk about springs, hot springs, geysers, and geothermal energy. Let's first take a look at springs. So springs, like the one that you're seeing up here, are sourced from zones of saturation of the groundwater. Ultimately, those zones of saturation are sourced from precipitation. This specific picture is in Thousand Springs State Park, which is about 2 hours from here, nearby Twin Falls. I haven't been, but I mean to go sometime this summer. I've heard it's just really, really cool what you can see there. Okay, so springs tend to happen wherever or whenever the water table is intersecting the Earth's surface. And it causes a natural outflow of the groundwater. So again, the process goes like this. It rains, that water infiltrates into the ground, it becomes groundwater, and then it basically flows horizontally through a layer and then is expressed as a spring at the surface where that layer that was carrying the water outcrops. So they often form when an aquitard is blocking the downward movement of that groundwater any further. So again, I'm going to go ahead and experience this one more time. So again, if you have the surface of the Earth, you have precipitation and the water is falling down, but suddenly there is an aquitard blocking the flow any further down, then the water is going to be forced to move laterally one way or another, right? So if suddenly the topography changes and you are forced, or the water is forced to basically outflow, it will do so as a spring, like the one that you're seeing here on the picture. So it's coming out over here because the downward movement is restricted by this aquitard below it. Okay, hot springs are basically the same thing as a normal spring, but typically for them to be considered hot springs, the water has to be 6 to 9 degrees Celsius warmer than the mean annual temperature for the locality where they occur. So if, for example, we take here the Treasure Valley, I think the mean annual temperature for the Treasure Valley is somewhere between 15 and 20 degrees Celsius. And so a hot spring would be considered a hot spring as long as it's between 21 and I guess 30 degrees Celsius for it to be here in the Treasure Valley. In the US alone, there are about 1,000 hot springs. Many of them are here in Idaho actually, which is super cool and really fun to go to. And not very far actually, so that's really nice. And as you know by now, hopefully, the way that these springs get hot is through the heat that is coming from high depths. So, as you know, temperature rises with depth, and we call this the geothermal gradient. As we know also, the average gain of temperature based on the geothermal gradient is about 25 degrees Celsius per kilometer that you go into Earth's depths. So, as the water circulates at some depth, it will get heated, and if it's able to rise fast to the surface after it gets heated, it will stay warm enough that the surrounding rocks won't cool it down for some time, and it will express itself as a hot spring at the surface. So many of the hot springs in the eastern US occur in this manner when the water flows all the way to some certain depths where it gets heated by the geothermal gradient, and then it flows rapidly back to the surface and expressing itself as a hot spring. However, about 95% of the hot springs in the US actually occur in the western US. In the case for the western US, the source of heat tends not to be just the geothermal gradient, but it usually has to do with heat from magma bodies that lie relatively close to the surface, or from the radioactive decay from some relatively young intrusive igneous rock, like is the case here in Idaho. So, as you know, in Idaho we have the Idaho batholith, which is about 65 to 100 million years old, so relatively young. And by the radioactive decay that is ongoing on some of the isotopes that are contained within the crystals of the batholith, there is energy that is being released. So in this case, the Idaho batholith is heating up the waters that circulate nearby it. So as I told you also, I went to Yellowstone a couple of times during my graduate school, and we did this to collect samples and to do some surface heat measurement studies with my research group. So the picture that you have here on the lower right is one of those experiences at which we are collecting samples from the spring, a hot spring I should say. And it's probably one of the coolest things that I have ever done in my life, one of the coolest areas and one of the most amazing experiences. So I highly recommend that you go there. And not just go to the main attractions or areas where the people go to, but also get a little bit off the beaten path and look at some of the other springs that are available.